Okay, guys, I assume that you've already, of course, read the problem and tried it yourself and are watching this afterwards, so I'm not going to reread the problem. We're just going to jump in. Okay, part A is how many cubic feet of rainwater flow into the pipe during the 8-hour interval. Okay, so in our model, R of T is the rate at which water flows into. So we're not even looking at D of T right now. Okay, now remember that's the rate, that's the derivative. Okay, so we want the antiderivative. This is the rate, cubic feet per hour. Okay, right? Feet cubed per hour. Well, if we go backwards, it's going to take away the rate. It's just going to be feet cubed, which is the amount of water. Exactly what we want. So we're going to do the integral from 0 to 8 of R of T dt. It's calculator active, so you simply type that in your calculator. Do not try wasting your time integrating that. It's not going to be very doable. We're going to be getting 76.570. And sorry, I'm using a different stylus, so it's not quite working great. Okay, and it is, we don't need units because they give it in the actual problem, but it always helps. Okay, that was worth 2 points. 2 points. Okay, part B. Is the amount of water in the pipe increasing or decreasing? Well, we have to be careful with the amount of water because water is flowing into it at a rate of R of T. So that's the rate at which it's flowing in, so that is the derivative, but it's leaving it at a rate of D of T. Okay, so this is the amount of water, the rate. So this is actually the derivative of the amount of water. And that's exactly what we want. We want to know if it's increasing or decreasing, so we want the derivative. These are the derivatives. These are the rates. So I'm going to plug in 3, R of 3 minus D of 3. I'm going to type those both in my calculator. No derivatives, no nothing, just literally plug and chug. And I find that I get a negative number, so it's decreasing. Now it says give a reason for your answer. I did. That's right here. Okay. That the rate at 3 is negative. Okay, part C, it says, I can go around. At what time is the amount of the water in the pipe at a minimum? This is the hard one. Okay, oh, by the way, part B was worth 2 points. Part C is 3. This is the one that a lot of people miss, is part C. Why? Because they don't check endpoints. Okay. So the amount of water that we actually have, well, we're starting with 30 cubic feet. So we're going to have 30 plus the antiderivative of that. So I'm going to write it as an integral of R of T, but I don't want to use T. Okay? Because they want T. So I'm going to use X. Get rid of that. Because I know that eventually I'm going to be using the FTC part 1. And I know that when I take the derivative, it's going to replace that variable and it will become R of T, which is exactly what I want. Okay. And then I have to minus the integral of the rate at which it's flowing out. So D of T. So I'm going to do the same thing. D of X, dx, 0 to T. Now you might be thinking, does it really matter about my variable? Absolutely. If they use T, you better be in terms of T. Okay. Because when I take this derivative, I'll call this F. When I take f prime, that's 0, the derivative of 30. But here, FTC, the derivative of an integral, is just R of T dt. Okay, excuse me, not dt, it's just R of T. Okay, minus D of T. So variables do matter. Okay, and I want to know when this equals 0, right? We take our derivative, set it equals 0. We're starting the first derivative test. I use my calculator. I end up getting T is about, well, 0 for starters, and 3.272. Okay, so I've got my places for my number line. So I've got my places I need to check. Could be mins or maxes. I don't really want to use a number line though, and I'll talk about that in a second. But I also have endpoints. Okay. Wants to know when the water is at a minimum. Well, we've got times at which it could be at a minimum, could be at a maximum. So we're going to kind of make a chart at the time and the amount of water. I'll just call that F because that's what I called it up here. Okay, that's an F. All right, so I need to check 0. I need to check 3.272, and I need to check 8. Those are my 0 and 8 are my endpoints. Okay, so I go back up here, and I know at time 0, that's the initial time, there are 30 cubic feet. So I've got that. It'll let me write it. Okay, the other ones I need to use this. Okay, you might be asking, well, do I plug it in for X? Do I plug it in for T? Well, remember, these are T times. So when I plug it into my equation, I'm plugging it in for T. Okay. So literally, I'm using my calculator and my integral command. Let's see, I end up getting 27.965. And when I plug in 8, I end up getting 48.544. Well, which one's smaller? The 27. So it says at what time? So they're looking for the T value. So my answer is T equals 3.272, and we were in hours. That was 3 points. Okay, 3 points. Okay, part D. So here we go. The pipe can hold 50 cubic feet of water before overflowing, blah, blah, blah. Right, but do not solve an equation involving one or more integrals that gives the time when the pipe will begin to overflow. Well, if you got the part in this beginning equation in part C, you pretty much have part D. But part D says, let's see, a time W. I kind of overwrote that, time W. So we don't want T, we want W. So my equation is 30 plus the integral. I want to be 0 to W. I'm going to use R of X dx again. Minus the integral 0 to W. D of X dx. Because once again, if I take the derivative, I want it to be R of W. That's what they tell me to use. Now that's the amount of water. Well, it will start to overflow when it equals 50. That's it. It said write but do not evaluate. And that was 2 points right there. 2 points. Okay, so there's your after school review 1.